Hello, my name is Guillaume St-Onge, and my presentation today will be about the localization, bistability, and optimal seeding of contagions on higher order networks. So first, I just wanted to introduce myself briefly. I am a PhD student in physics at Laval University, and I should be done by the end of 2021. So this is my first time at the Alife conference, and I'm really excited to meet you all and learn more about your work. I'm always looking to expand the scope of my research in complexity science, and I think the Alife conference is a perfect venue for that. Obviously, this is a recorded talk, but I will be present in the chat to answer any of your questions during the presentation. I first want to give a very general perspective on the modeling of complex systems using the tools of network science. So first, the elements of the complex system usually have a state that could be continuous or discrete. For instance, if we're considering a neuronal system, it could represent the neuronal activity of the neurons. In a social system, it could be the political allegiance of the people, or in an ecosystem, the species abundance. But when we want to model complex systems, we also want to consider the structure of the systems. And the simplest way to do that is to consider pairwise interactions between the elements, leading us to network structures. And these pairwise interactions could represent the synapses between the neurons, for instance, or a friendship relationship, or a predator-prey relationship. And this is really a useful representation, but sometimes we want to consider a more general type of interactions, leading us to higher order network representations. So instead of considering interactions between pairwise of elements, we will consider interactions between groups of elements. And these interactions could be, for instance, a complete workplace environment or an ecosystem. And there are various ways one can represent a higher order network. It could be using a hypergraph or simplicial complexes. During this presentation, I will just consider a simple bipartite representation with the nodes and the groups to which the nodes belong. My current research focuses on contagion dynamics, and I know that with the current situation, most of you are probably more aware of how we do the modeling of these systems, but I still want to introduce some basic notions. So in this presentation, I will only consider that the agents of the systems can be either susceptible or infected. And the simplest way to model the system is to consider what we call standard epidemiological models, where there's no structure and every agents can interact with each other all the time. Building on top of that, we can consider network epidemiology, where we consider a network structure to represent the interactions. And we could stop at this level. It could make sense, because the transmission events, at least for biological contagions, the transmission events are only the results of these pairwise interactions. But if we consider, for instance, a social contagion, where you have the spread of a rumor or there's a rise of a new social movement, well, it is always the result of a concerted group of agents in the systems. So it makes more sense to use a higher order representation in this case. And I would argue that this is also a good representation for biological contagions, due to the fact that the pairwise interactions are always the results of these group interactions. Let's say if you go to the hospital, the workplace, or to a school, for instance. Although the subject of my research is about contagion dynamic, the goal of this presentation is first to promote the higher order network representation of complex systems. And I also want to introduce an accurate method to describe stochastic dynamics on these higher order structures. So first, I will present to you what we call the approximate master equations framework. And then after that, I will show you some applications of this framework to contagion dynamics. As with all compartmental formalism, we want to create a partition. In this case, not just of the nodes, but also of the group. In this case, we want to partition the nodes according to their membership and their state. And we will also partition the groups according to their size and the number of infected nodes in the group. An important assumption underlying such formalism is that the bipartite structure that we have is the result of some random matching process between the nodes and the groups. With this formalism, we are able to consider very general transition rates For instance, for the infection of a node within a group, we can have a function that depends on the number of infected nodes and also on the size of the group. We can do the same for the recovery rate that can also depend on the number of infected nodes and and the size of the group. But in general, for contagion dynamics, we only consider a constant recovery rate. In mathematical terms, this is what it looks like. The details of the equations here are not really important. I just wanted you to see the form of it. So to describe the number of susceptible nodes with a membership M, we define the variable Sm, and we use a mean field equation to describe its evolution. Since we are interested in group interactions, we want a much more detailed description for the groups. So we track the number of groups of size n with I infected nodes in them. This results in an approximate master equations because the local transition rates here shown in blue are described exactly, but the coupling between the different groups is approximated by a mean field term here shown in green. Let's now move on to some application of this framework. Even if we consider some simple contagion dynamics, where the infection rate of a node within a group is just proportional to the number of infected nodes within that group, we observe some rich behavior. For standard epidemic, we expect something similar to what we observe for the delocalized regime. As we increase the transmission rate lambda above a certain threshold value, a macroscopic portion of the system gets infected. The dashed lines represent the global fraction of infected nodes in the system, while the solid lines give the fraction of infected nodes within groups of a certain size. And as can be seen on the right, for a certain value of the transmission rate, the distributions for the fraction of infected nodes is pretty homogeneous, regardless of the group size. In what we call the mesoscopic localization regime at the bottom, however, we have a completely different scenario. Above the epidemic threshold, only the largest groups support the epidemic, while most of the groups are effectively in a subcritical phase, as can be seen on the right. And an interesting aspect about this approach is that we can get some analytical results, and these results gives us some really meaningful insights on the role of these higher order structures on the dynamics. And in this case, it is able to give us some insight on when we should expect to have a localization regime for the dynamics. So if we use a parallel distribution for the group size and a parallel distribution for the membership distribution of the nodes, then we obtain the phase diagram on the left that gives us a clear picture of when we should expect localization, represented by the green portion. And an interesting aspect about this phase diagram is that the blue portion on the bottom left, all the networks in this portion are expected to be dense, so we expect that most of the real networks fall into the mesoscopic localization regime, which is the green portion. Also, then we can just refine the analysis and, for instance, change the dynamical rules or consider the effect of finite cutoffs, as we have done on the right. And you can see what's the impact on, let's say, the boundary separating the two localization regime in this case. Now, if we consider some more complex contagion dynamics, it opens the door for a lot of rich behavior. So to motivate the introduction of a non-linear interaction terms for the infection of a node within a group, let us place ourselves in the context of a social contagion. Let's say that, for instance, the contagion is a trend. And well, if many of your friends adopt the trend, you could be less interested to adapt it to remain original, like in a hipster way. And this would be best represented by an inhibition effect. On the contrary, you might be more willing to adopt the behavior if a large portion of your friend adopts it, in which case it would be best represented by a social reinforcement effect. And we see that when the social reinforcement effects are strong enough, this can lead to a bistable region where two solutions coexist. One where a certain fraction of the system is infected, and another one where none of the agents in the system are infected or all are susceptible. Again, with our approach, we are able to really predict accurately when this should happen for a certain type of higher order structure. But I think the most interesting aspect about nonlinear contagions dynamic is when you consider the problem of influence maximization or the optimal seeding problem. So let's say that your goal is to maximize the early spread of a contagions by choosing wisely which nodes you can infect in the system. So this could be the result, for instance, of an advertisement campaign where you want to optimize the number of people that you will reach with your campaign. So let's assume that we are in a regime where we assume that the epidemic will take off as soon as we infect a certain portion of the system. And you can choose between two strategies. The first strategy, the influential spreader strategy, is to find the nodes in the system that will maximize the early spread. So trying to find the influential spreader only based on the membership of the nodes. What you can do instead is try to find the influential groups in your system and try to engineer the configuration of the groups at the beginning such that it maximizes the spread early on. And as I said earlier, since we assume that the higher order structure is the result of a random matching process, if we choose to engineer the nodes, well, the configuration within the groups will be random, and if we choose to engineer a configuration, well, the nodes will be distributed at random. To clarify this a bit, on the left we have the influential spreader approach. And it can be shown that for most contagions there is an optimal strategy, which is simply and quite intuitively to infect the nodes with the highest membership in the system. And when we do so, the configurations within the group will be distributed at random. On the right, we have instead the influential groups approach. And it can also be shown in this case that there's an optimal strategy, which is to favor a certain type of group configuration. But when we do so, the infected nodes within the systems won't necessarily be the ones with the highest membership. And what is really interesting about this problem is that we can see that targeting the influential groups becomes much more important than targeting the influential spreader as soon as the contagion becomes sufficiently nonlinear. And this new intuition could help us design more efficient strategy to, let's say, diffuse information, or if we take the reverse problem, we could design more efficient intervention strategy to minimize the spread of a contagion. So I hope that this presentation got you interested about the use of higher order network representations to study complex systems. There are lots of mathematical framework out there that can be used. They're usually really flexible and you can use them with the various types of dynamical processes. For instance, the approximated master equation approach that I presented you could be used to study water models or any evolutionary game theory related models. So if you think that this type of approach could be used to study your problems, just let me know, contact me and we can have a chat about it. I finally want to acknowledge my collaborators on these projects. So on the epidemic localization project, there's Vincent Thibault, Antoine Allard, Luigi Dubé, and Laurent Berdufresne. We also have 2 preprints on this subject, so if you're interested about it, you can check them out. And on the bistability and influence maximization or optimal seeding problems, Jacopo Jacopini, Giovanni Petri, Alain Barra, Vito Latora, and Laurent Berdufresne. And I also want to thank the funding and computational resources that made this research possible. Thank you very much.